Hi, my name is Daraja Brown, and this is my Lab 5, Magnetic Braking with Faraday. So the purpose of this lab is to observe a falling magnet through an aluminum foil tube and then to analyze and interpret that data. And finally, we will create a computational model of the experiment and then compare the experimental and model data. So the main principle used in this is Faraday's law, which has these three resulting equations. So the first one is how to calculate flux. The second one is the magnitude for the derivative of flux. And then the third one is that the dot product of the electric field and then the changing distance of the loop around the whole loop is equivalent to the negative derivative of the flux. And then the magnetic force is calculated as IL cross B, where I is current, L is length, and B is magnetic field. And then we will make our computational model with WebV Python. So the main results, the average time for the magnet to travel from the beginning to the end of the tube was 0.688 seconds, and then the modeled predicted time for the magnet to fall through the tube was 0.456 seconds when we used a magnetic dipole of 1.492 am squared. And then we needed a magnetic dipole of 2.204 in order for the observed and modeled times to fall to align. So the system in this experiment is obviously the magnet, and then the surroundings are both the Earth and the aluminum foil tube. And our initial conditions are that the magnet is at rest at the top of the tube, and the force of gravity and the force from the aluminum foil tube are what acts on the magnet. So the experimental procedure was to first mark and measure both the magnet and aluminum foil tubes. Then we drop the magnet through the tube 5 times while recording at each time the fall times. And then we use that to determine the individual and average fall times. And then, as we previously stated, we modeled the whole experiment with WebV Python. So the results, the individual fall times were 0.68, 0.72, 0.69, 0.69, and 0.66 seconds, giving an average time of 0.688 seconds. The magnet mass was about 0.024 kilograms. The length of the tube was 0.44 meters. The inner radius was 0.0133 meters. Outer radius was 0.0165 meters, meaning that the foil had a width of 0.0032 meters. And like I stated, we initially used a magnetic dipole of 1.492. So here we can see our coding. This has different values plugged in order to make the code accurate to this experiment, as well as creating some equations. So here's some more code, a lot of lines. And after 195 lines of code, we plotted a curve showing the velocity versus time. And these are the results. So on the left, you see that tube and kind of is modeling how the magnet goes through it. And then on the right has a velocity versus time graph, which just has a horizontal line. So I think something with the plot got messed up, which we'll discuss in a moment. So similarities and differences. The magnetic dipole moment originally used led to a much quicker fall in the computational model than observed, and which means that we needed a larger dipole in order to match those fall times. So some possible sources of error, as we saw with the graph, there could be additional forces than just gravity and the magnetic force that would cause the magnet to fall, and there could be also timing inconsistencies since the times were recorded by hand measurements. So what if the resistivity of the conductor were reduced? How would that change the dynamics of the magnet? So then the resistance would decrease drastically, leading to a slower fall because there would be a less negative net force in the negative y direction. And then what if we added holes or slots in the tube? This would mean that the induced current in the foil would decrease, which also means that the magnet would fall quicker, since lower current leads to lower magnetic force, which means we would have a stronger net force in the negative y direction. So in conclusion, there are many factors that affect magnetic force between objects, which then affects the object's behavior. And we can also always explore force interactions and magnetism using household objects in a strong experiment and procedure. Thank you.